So here's another application of the mechanical energy conservation principle. In this problem, okay, apart from the fact that we'll use MEI equals MEF to determine the speed at the bottom, there's some other things also that it's important for you to learn. Okay, so what's happening in the problem is that there's a mass that is attached to a string that is attached to the ceiling, and this mass is released. Initially the string makes an angle theta, and this mass is released, and we're going to find the speed of the mass at the bottom of this arc. Okay, now if you can find the speed at the bottom, you should be able to find the speed at any point in its path, and I would recommend that you try that out. Okay, so let the initial angle be theta. I'm going to let go, and it's going to swing, and as it swings along this path, okay, we're going to find the speed at the bottom of the arc. Now again, we're going to use conservation of mechanical energy, since there are no resistive or dissipative forces, so no non-conservative forces, so MEI equals MEF can be used. Okay, so let's use MEI equals MEF. Let's figure out what we need to do. But by now I hope you understand that to use MEI equals MEF, we need kinetic and potential in the beginning, kinetic and potential at the end, and then we equate the two. So in this problem, the only tricky thing is to figure out the initial height. Now if you know your basic geometry, if you remember what you need to do, then life's very simple. But I noticed that this happens to be a problem where people have a lot of trouble. So let's see how to go about doing this. So what we'll do is, if you look at this problem, okay, the object is initially at this location, and what I'm going to do is I'm going to redraw the picture. So this is the length L, and then draw my vertical line, and it goes down here. And what we know is that this length from all the way from the top to the bottom of the circle is also equal to L. Now this is important. Okay, we'll use this in a second. Now what we know is that the initial height of the problem, the initial line height is that, and then the final line height is somewhere here. Okay, and if we know this height h, then we're good to go. So the key here is determining this height h, given that this angle is theta and this side is L. Now we can use basic trigonometry here to identify this side. Okay, let's just call this side y for now. And if you look at this triangle, y is the adjacent side to the angle theta, so I could use y over L equals cosine of theta, and this gives me y equals L times cosine of theta. Once I know y, it's very easy to find h. If you look at the picture, h is nothing but L minus y. So it is equal to L minus y. And now let us substitute for y, and you get L minus L cosine theta. Understand the process here. What we did was, we said, okay, the block starts at the height 1 here and goes down to height 2. Okay, and what we know is that the length from the top of this string to the bottom is L, and that length is never changing. So as it goes down, we realize that, hey, let's figure out this height h. And once we know the height h, then in order to find the height h, we needed to figure out this y out here in the picture. Once we get y, then the height h is simply equal to L minus y. Once you know the height h, the rest of the problem is very simple. So in the beginning, we have no kinetic energy, and we have potential energy, which is equal to m times g times this h, which happens to be mg times L minus L cosine theta. Now here you see I can factor out the L, and I can rewrite this as mg to L times 1 minus cosine theta. So that's what I get. Now at the bottom of this arc, the final mechanical energy is equal to simply the kinetic energy plus 0 for potential. Alright, let's equate the two, and what you get is 1/2 mvf square is equal to mg times L times 1 minus cosine theta. And so from here, what I can do is I can find Vf, and Vf happens to be square root of 2 mg L, actually no, there is no m, the m's factored out, is equal to square root 2gl times 1 minus cosine theta. Alright, we have our final velocity. That's it for this one.